Okay, let's get started. Okay, we start? Great. So just one quick announcement from me, and then I'll see if Al has anything. If you guys have started on the project, ignore the linearity specs. Turns out they're impossible. So thanks to Al for catching that. That's good. We'll modify the specs in the coming weeks, but certainly I encourage you guys to get started, get the simulation framework up and running, get a simple design going, LNA mixer, run some simulations, make sure you know what you're doing. Don't, waste too much time with that stuff. Okay? And any other announcements? Okay. Any questions before we start today? All right. So this lecture, we're going to continue on mixers. It's our last lecture on mixers if we can get through the material. And today we're going to start out looking at passive mixers. And the distinction between passive mixers and active mixers is there's no conversion gain. Or the conversion gain is actually negative, so there's conversion loss. And typical loss numbers might be anywhere from a few dB to about 10 dB. So you might say, well, that's terrible. That's a lot of loss. Is that, how do you deal with that? Well, as we'll see, these passive mixers tend to be very linear and sometimes also very low power. So even though they have loss, they're very linear. And so you could put lots of gain in front of them because they're linear, or likewise put gain after them. So they're actually quite useful and used quite often. So let's just start off and see what a typical passive mixer looks like. Let's look at a voltage switching mixer. So the idea behind a voltage switching mixer is I have some differential voltage, and I'm going to basically run this to my IF port. So this is my IF port. This is my RF, plus RF, and this is minus RF. And I have switches here. So this switches, let's say, at LO, and this switches at LO bar. So at any given time, my RF input voltage is applied to the output with either positive polarity or negative polarity. And this is plus minus, this is plus minus. So you can see that during the plus LO cycle, the equivalent circuit is just RF applied directly to my IF. Right? During the negative LO cycle, then I have this side grounded, and then this is connected to RIF. And so we can see that this circuit is very simple. It just multiplies the RF by plus or minus 1 at the rate of the LO period. So it looks a lot like some of the other mixers that we've seen before. Okay? So what we need are good switches. Because now you can see that if these switches have on resistance, then we actually form a voltage divider between the input and the output. Okay? Any questions about that? Exactly, that's where the loss comes from. And you can see that this circuit has no gain, right? It's just switching in and out different voltages. And so as we've drawn it, it does not have power gain. Yes, Firas.
I mean, what's the so MEMS switches are only for like high Q. Do they have other advantages? Are they used for like this application? Can we use them for this application?
They're not used for this application very widely. One of the reasons is that it's hard to switch MEMS switches very rapidly. We want to switch these things in at a rate of a gigahertz. So that's one limitation of a MEMS switch. The other limitation is reliability. If a MEMS switch, there's many ways to build MEMS switches, but if it's something like an electrostatic switch, then you're basically making contact between two metals and breaking the contact, a billion times a second. And there's a reliability concern on how many times can you switch a MEMS switch before it fails. So that would be a mechanical mixer. You could build one like that, but they're not really used today. Okay. All right, so let's look at a version with MOS transistors. So naturally, I'm going to use an MOS device, and I'll include some source resistance this time. Let's say this is a differential RF voltage, and this is a complementary LO signal. And in this case, that there's source resistance, you can see that even if the switches are perfect, even if the on resistance is 0, there's going to be insertion loss because of this voltage divider effect. So this circuit uses MOS devices as switches. So we want large W and small L so that we have low on resistance. On the other hand, we want small w for low feed-through capacitance. Right? When I turn this device off, what's the equivalent circuit for this device when it's on and off? So let's say an on MOS device just looks like a small resistance. This is R on with some, let's say, substrate parasitics. An off MOS device, well, there's also our gate. So this would be CGS and C gate to drain. And there'd be more or less symmetric because this voltage is very low, so this device is in triode region. An off MOS device, there is no channel, but there's basically the same network. So CGS, C gate to drain. So now these are overlap. So let me put -O. There's C gate to bulk, and then there's also the drain junction, source junction, and R sub. And so you can see now that there's a couple of issues. One, because the LO has finite on resistance, let's call this RLO, there's going to be feed through from the RF signal to our IF port. And there's also feed through the substrate network. So that feed through depends on the size of the devices. The larger we make our devices, the more feed through. On the other hand, the larger we make the devices, the smaller the R on. So there's a compromise here for device sizing. Okay, any questions? Yes, David. Actually, sorry, your name's not David, is it? Okay. You don't write David when you turn in your homework, so. Okay, sorry.
So why would you want to use small R-ons for this? What if you want to match the impedance? Split 40 and 10 for 50.
Basically to minimize the insertion loss, right?
If you want to maximize power gain, what if RIF is 50, RF 40, then you left 10 ohms for the switch?
Well, look, here's one way to look at it. If we come back here, if this were no resistance, right, I could design a matching network so that this source resistance is matched to this resistor here, right? On the other hand, any resistance I put in here is extra power lost that's not getting to my load, right? So you could, but it's still, you know, there's going to be some current flowing through here, right? And no matter how you look at it, the power loss is I squared R, right? 1/2 I squared R for a sinusoidal signal. So you want to minimize the power you lose in that switch. Okay. Debo?
So if the LO signal is not made very large, can't we make it look like a common gate amplifier?
Yeah, and then it wouldn't be a passive mixer. Yeah, good question. That's a different kind of mixer. So one of the issues with a MOS switching mixer is you need a very large LO drive to turn on the devices on and off. Okay? You also need to bias these appropriately. For instance, a good bias point might be to bias these devices near threshold. So that any positive LO turns it on, any negative LO cuts it off. So I haven't drawn the DC biasing here. All right. Any other questions? Well, another issue with this is how do we create these differential signals? In one approach, we may need, so let's just say, need to create differential RF and LO signals. And commonly we do that with a balun. And as we talked about last lecture, baluns are typically bulky and limit high frequency performance. But they're very convenient in this application. So for instance, I could come in with a single-ended RF, convert it to a differential RF, actually pick the right bias point for my switches if it's not ground, and I could likewise drive these gates with a single-ended LO. But usually your LO can be made differential. You're going to have a differential LO buffer, so that's less of an issue. Okay? Okay, well, in fact, a more popular version of this mixer is, actually, before I do that, let me say a couple things about noise and distortion. Distortion, so let me just say that these devices, so passive mixers, MOS passive mixers, are very linear. Okay, why can you make that claim?
R-on is very linear.
Do you want to use the mic?
R-on is very linear.
That's right. R-on is a very small resistance. Even if it were nonlinear, it's a small contributor to the overall transfer function. So basically the fact that we're using the transistor as a switch means that it's going to be pretty linear, right? When it's off, it's just a linear capacitor. There's some nonlinear junction capacitance, but that's, you know, that's not too bad. And when it's on, basically it's just a small resistance. And hopefully it's a small resistance and it doesn't contribute significantly to loading, and therefore it has a pretty minor impact. Okay? But even if you look at a MOS transistor in triode region, if VDS is pretty small, it's a pretty good linear resistor. And you might guess, because of the differential operation, you could easily hook things up to cancel out the second order nonlinearity. So being a square law device means that you can even in fact get rid of some of the square law distortion. The noise is okay. It's lossy. That means the noise figure is going to be at least as large as the attenuation, right? Plus the noise folding. But at the same time, if you think about the intrinsic noise of the device, again, it's a small resistor. So when it's on, it contributes a little bit of resistance, so a little bit of thermal noise. And when it's off, it contributes essentially no noise. Okay. All right, any questions about that? Yes?
What limits the linearity of passive mixer? Is it the charge injection? Is it?
It's actually quite complicated. If you're interested, I can send you a PhD thesis on the topic. Because it's pretty linear to begin with, to really get at the nonlinearity, you have to dig deep and look at. So you could do Volterra series analysis on the device, nonlinearities. It's the nonlinear junction cap and also the nonlinear behavior of a short channel device. It's not perfectly square law. So all these things contribute to the nonlinearity. Yeah. Okay. Any other simpler questions? Okay. Well, actually it's also pretty common to do a ring style mixer. And a ring mixer looks like this. It's 4 transistors in a ring. And what I'm going to do is I'm going to inject a differential RF signal here, or if you like, a floating RF signal here. I'm going to take my IF signal here, again a floating IF, and then I'm going to apply my LO here, and LO bar here and here. Okay? And you can see that this circuit looks like a, again, the equivalent circuit is that when LO is high, let's say, then RF is connected to the output through this network, right? And when LO is low, then these 2 transistors turn on, and the RF is supplied to the output with negative polarity. So again, this is a fully balanced mixer. RF gets multiplied by plus minus 1 at LO rate. Okay? So it's a fully differential version of the mixer that we just looked at.
Is this just size, like advantage? We just have smaller size for the ring mixer?
No, it's the advantage of a fully balanced mixer. Yeah. So what can we say about this? So this mixer is fully balanced. It has, let's say it has all the good properties of previous mixer. It requires 2 times the capacitance. So if you're driving this, usually you're going to have an LO buffer. Let's say it's an inverter chain. Because you have twice as many devices, you have twice as much capacitance. How much power does it take power to drive the LO port. How much power does it actually take? Well, because it's mainly capacitive, then we know from, let's say, 141 that the power is CV squared F. This is the power to charge and discharge this large LO capacitance. Okay? That's if we drive it with, let's say, a square wave. What if we drive it with sinusoids using a tune circuit? For instance, I can have a tune circuit that absorbs the LO port capacitance. So this is partly CLO. And I drive it as a sinusoidal network. Well, then the power depends on what the effective resistance is. Let's say the tank resistance. So the power would be V squared over 2 R tank. Right? And the quality factor of this tank is omega RC, R tank CLO. So I can substitute for R tank as Q divided by omega CLO. So then the power, the LO power required would be V squared over 2 Q times omega CLO. In other words, it's pi CLO V squared F divided by Q. Okay? So if I compare these two expressions, you can see that for a fixed LO drive, and also a fixed LO frequency, that driving it with a sinusoid can actually reduce the power if I can get quality factor high enough. So high Q tank has lower LO power. Okay? And the more capacitance I have on the LO port, the more power it's going to take to drive it naturally. Well, here's another version of a mixer. Let's call this one the H-bridge ring mixer. And it uses NMOS and PMOS devices. So in effect, we're going to use basically a CMOS circuit, fully differential CMOS circuit. And we're going to drive this again with our RF signal here. And I'm going to take my IF across here. And this port I'll drive with the LO, and this port I'll drive, let's say, with an inverter and LO, or LO bar. And again, the circuit works the same way. Flip the order, so put the NMOS over here. No, because then it becomes a Class AB driver stage, right? So then it would take the LO and basically the output would be like a follower. So when the LO is positive, the LO would appear at the output. So we don't want that. We want the LO just to control the on resistance of these devices. Okay. Let me show you some ways that you could also drive this circuit. We've been driving some driver stage. Let's call it the RF driver stage. You know, we've been drawing these floating RF stages. One is to use a balun. Another one is we could use basically a matching network to try to maximize the voltage swing at the RF port. And instead of drawing the mixer as a ring, I can just draw it as follows. These are, let's say this is the all NMOS version. So this is LO, this is LO, this is LO bar, this is LO bar. And let's say this is our IF port. And this is our input voltage. So this is our source impedance divided by 2. So I have a differential signal coming. This might be coming, let's say, from a differential LNA. And what I do here is I have a matching network in order to maximize VRF. Let's call this voltage VRF. Okay? And so I can decompose this into an equivalent half circuit. I have Vin over 2, RS over 2. I have some AC coupling, so this is nothing. Then I have an, let's call this L1, this L2, this L3, this L4, this R1, okay? And let's call this C3. So I have first a matching network, L1, C3 prime, and then I have a tank, L3, C3 double prime, where C3 prime plus C3 double prime is actually equal to C3. So you can see here that this is really an L matching network, and this is a tank. So what I'd like to do is resonate out all the capacitance at this node and apply the RF voltage as large as I can over here. And I know that this L matching network can take this voltage and boost it by the quality factor of the matching network. Remember, this is a series resonant circuit. So in resonance, the current in the circuit flows through the source and through the series reactances, and the voltage across these series reactances is Q times bigger than the voltage across here. And since in resonance the voltage across here is all applied across here, we get a Q boost in the voltage. Right? Okay. Any questions about that? So the voltage gain of this stage is equal to roughly, let's say that in resonance I see R tank looking to the right. I'm going to see R tank divided by R tank plus the source resistance. If I look back here, the source resistance is boosted by 1 plus Q squared because of this L matching network. And the voltage here is boosted up by effectively Q, or more exactly Q squared plus 1 square root over here. So this is VRF is equal to this thing times Vin. And of course the Q of this circuit is just the reactance in the circuit divided by the source resistance. So the total reactance is L1 plus L2 for the differential circuit, and the total resistance is RS. So this is L1, L2, this is RS. Okay? Now, to analyze this circuit, it looks like a very simple equivalent circuit would be I have some RF voltage which is generated by this circuit that basically sees the following circuit. Where I've replaced each MOS transistor with a time-varying conductance. which is of course periodic. Okay? So if the conductance of this resistor is G of T, remember this one is driven by LO and this one's driven by LO. What's the conductance of this device and this device? Exactly. It should be the same, just a delayed version, if you like, or an time-advanced version. Because it's periodic, it's just the same conductance time-shifted. Okay? So this is the equivalent circuit, and this is basically my load capacitance. Remember, for a down conversion mixer, I'm going to put a filter at the output to pick off the down converted component. And so now I can basically write some equivalent Thevenin equivalent voltage and some Thevenin equivalent resistance driving the load. So from the load's perspective, if I look back, I just see some equivalent RF voltage VT and some equivalent source, let's say GT. Okay? And the Thevenin voltage is basically the voltage divider, this voltage divider minus this voltage divider. So this first voltage divider is G of T divided by G of T plus G of T minus TL over 2 minus this voltage divider, which is G of T minus TL over 2 divided by the same denominator, which all times VRF. And so this simplifies to G of T minus TL over 2 divided by G of T plus G of T minus TL over 2. Okay? And so really, we could say that VT is equal to some M of T times VRF, where M of T is our time-varying transfer function, right? And ideally, of course, we'd like it to go plus minus 1 at the rate of the RF. Okay, any questions? Yes?
Two matching questions. One is how critical the matching between L1 and L2 in the circuit. Number two is how critical the timing for the pi over 2, or pi, I guess.
Yeah, they're actually both important. All the good properties of the mixer come about if you assume perfect matching, right? If you have perfect matching, you can reject the LO port noise, for instance. If you have basically flicker, if you have basically any kind of jitter in the clocks, any kind of mismatch in the clocks, then you will not have the good properties that the waveform has 0 DC value, that the waveform is half-wave periodic, symmetric. So all these good properties which lead to good performance depend exactly on having good matching, good waveforms. So it's very critical when you design these kinds of mixers to drive it with 50% duty cycle LO, be very careful that all the paths are matched, and so on and so forth. Okay? Any other questions? Okay. Well, this one is kind of a passive mixer, but it's a very related beast. So let's call it, for lack of better name, a passive current mode mixer. Okay? You might object and say we already studied a passive current mode mixer. The Gilbert cell, if you take the transconductance cell away, is also more or less just a current commutating mixer, right? But what we're going to do is we're going to take almost the same exact circuit and basically run no DC current through our Gilbert cell, or let's say our Gilbert quad. So we're going to have some input transconductance stage to convert our voltage into a current. I'm going to have a high impedance load, so basically I'm going to push all my RF current into the mixer. And so this is what the full circuit looks like. So let me drive these ports with LO and these ports with LO bar. So the idea of this mixer is there's no DC current in the switching quad. So very similar to the voltage switching mixer, I just turn these devices on and off. They go into triode, they go into cutoff. Okay? And there's no net DC current flowing in here. Now the AC current will flow into the switching quad and basically will get commutated either positively or negatively, just like we saw in a regular Gilbert quad. And then that current will flow into this virtual ground. So this is a virtual ground. And then through this feedback impedance, RF, to produce an output voltage at IF. Okay? Now, let's talk about some of the advantages and disadvantages of this mixer. First of all, let me make sure that everybody has a idea of how it works. Any questions about how it works? Yes, Thibault.
So why do you call it a passive mixer?
That's a good question. That's why I put passive in quotation marks, so I could just say, well, it's kind of passive. It's the reason is that we're not running DC current through this Gilbert quad. So I want to distinguish between the Gilbert mixer.
But the GM at the RF stage is still
Yeah, this is still active, and I can actually get power gain out of this mixer. You could see that to first order, the gain of this mixer is GM times RF times, let's say, 2 over pi, the switching function here. Yes?
Choose the benefit of using a transmission gate for the switches in the quad.
You could use transmission gates, yeah. I haven't seen too many people using it. Maybe that would be a good thing to try out for your project. See what the benefits could be. Yeah, it's a good project idea. Okay, so kind of the key point is no DC current in quad. And can anyone think of an advantage of not running DC current through that quad? Exactly, no flicker noise. Okay. In general, because of the nature of this mixer, you can show that ideally there is no flicker noise due to the switching pair. But any kind of mismatch in the switching pair, which is a fact of life, does generate flicker noise at the output. So in direct conversion receivers, this flicker noise is a major problem. It's large and it can easily swamp out our signal. So if we can eliminate this flicker noise, it's actually a big benefit. So this is a big deal about these mixers. Okay. Now, one of the disadvantages, let's say comparing it to a Gilbert cell, we need a much larger LO drive. That's because in a Gilbert cell mixer, the amplitude just needs to be large enough to switch currents back and forth, and all the devices can remain more or less, they're in saturation. Here, we're actually completely switching the device off into cutoff and then switching it hard on in triode. So we need a larger LO swing to do that. A big advantage is linearity. That's because after you get past the GM stage, so basically you have your GM stage nonlinearity, then you have your switching pair nonlinearity, or your switching quad, which is pretty linear. And then the output over here is a current signal. So the current flows into this virtual ground and then flows into this feedback resistor, which produces an output voltage. Because the output voltage swing is very low at this point, because of the low impedance, it's actually extremely linear. And this feedback resistor is just a passive resistor. And so overall, this last stage is also very linear. It's an op-amp with feedback. So the overall linearity is very good. It's just dominated by this input stage. Okay. Now in a Gilbert cell mixer, if you think about it, the output would be a large resistance. It would be a high impedance load. And so there would be a substantial voltage swing at the output. And we would have a big problem because that on a low power supply voltage, so let me draw a picture. So let me just draw half of the Gilbert quad. So let's say that we have the same GM kind of nonlinearity here. That's comparable. Let's say we also have the same kind of nonlinearity through this LO stage, but then at the output here we have a large voltage swing, right? And so that will generate nonlinearity in the transistor. It'll limit the voltage swing. So if I'm designing this mixer, I either have to limit the DC current or I have to limit the size of this resistor. But at the end of the day, I'm restricted by how much current I can actually swing because of the voltage. Over here, I don't have a similar limitation because I can swing a large current here, and since it's a low impedance node, there's no voltage generated. I only have to worry about voltage swing at the output of this stage. Okay, so it decouples the problem. So here I have the full supply voltage available to me, whereas in this case I only have a limited supply voltage available to me because of the headroom taken up by these devices. Okay. Even if I use an inductor as a load here, I still have the headroom of these two devices. And recall that the output here is at IF frequency, at a lower frequency. So I would need a very large inductor to act like a low-pass filter, which is usually not practical for a low IF system. Okay, any questions about that? Yes?
What about the op-amp that you had on the final stage?
Yeah, you kind of moved the problem to the op-amp. But remember, the op-amp, in theory, you can build a rail-to-rail op-amp, right? So you've basically moved the issue of voltage swing to the op-amp. If you have a multi-chip solution, you could also potentially run the op-amp on a higher voltage. Because this, remember, this is an IF stage. So you could use longer channel length devices, thick oxide devices, run this off a higher supply voltage, maybe 5 volts. Maybe this here works with 3 volts. And you can even get even more performance out of that. Okay, so it somehow decouples the problem. There are some disadvantages. So one of the big disadvantages, we need this op-amp to convert current signal to voltage. And you also need common mode feedback. Because it's a fully differential op-amp. So in a way, the current that we saved here, we pretty much have to burn here anyway. So there's really practically no current saving. You're going to need to run current through here. You're going to need to run current through here. And to create a low noise op-amp, you're actually going to need to burn a substantial amount of current here. And you need a large LO drive. So from a power consumption perspective, there's actually no win. It's really the voltage headroom that's the biggest advantage that you get. Okay. Kind of an interesting point is it's kind of funny that a lot of things look different if you draw them a certain way, but they're actually the same thing. So let me just draw, let me call this node 1. So this is driven by LO, and this is driven by minus LO. Let's call this node 2. Let's call this node 3 and this node 4. So let me now show you guys. Let me just redraw this. Let me unwind it, right? You can almost see it, right? If I just take this thing, rotate it around, and flip it, what's going to happen? You're going to get a ring. So let me show you that. Let's call this M1, M2, M3, M4. And so let me draw M1 here. M1 goes from node 1 to 3. M2 goes from node 1 to 4. So I'll draw that here. M3 goes from node 2 to 4. And finally, M4 goes from node 2 back to 3. So really, this is a ring. So I bring in my input from one side, and I take my output from the other side. And basically, the first thing we looked at was I could voltage drive this ring, and this would be my output. Now we're kind of current driving this ring. I'm injecting a current and taking a load current at the output. So really, the Gilbert quad is the same as a ring. Okay. Questions?
Do you want to hook up the LO differently?
This is LO bar, right?
But I think you want to.
This port here? Okay, yeah, maybe I screwed this up, but it's fine. But believe me, it's a ring. It's the same thing. There is one big problem with this circuit, and that's the op-amp noise. So let's see how that comes about. Okay, I have this op-amp. And it's driven by this time-varying circuit here. So let me bring this out like this. And naturally, there's some parasitic capacitance sitting here. Let's call that CP. There's always going to be some parasitic capacitance sitting here. If I look back out here, it turns out that I see a resistance. Let's call that RP. Okay? Where does that resistance come from? It actually comes from charging and discharging these capacitors. If you're familiar with switch capacitor circuits, this is how we build a switch. Basically, this is how we emulate a resistor using a switch and a capacitor. So, very simply, if I have a switch, and let's say a voltage V in, and this is switching at some frequency F, right? When the switch is closed, I charge this up to V in. Okay? And let's say that when the switch is open, I discharge it. So let me put another switch to ground here. So if I do that, then the net current coming out here is going to be the total charge divided by the time that it's charged and discharged. So the charge is C times V in, and the time over which this happens is F. So V in over I in is basically 1 over CF. And notice the same thing is happening here. In this circuit, I'm charging, if I put a voltage source here, on one cycle, I'm charging this one positive, this one negative. On the other cycle, I'm charging this one negative and this one positive. So effectively, the same thing is happening. I'm charging and discharging a capacitor at a periodic rate. So you can do some simple analysis here. So this is LO, this is minus LO, and this is the voltage. So during one cycle, this gets charged to Vx. I actually need to reference this to ground. So let me do 2 and ground here. So during one cycle, I charge this up to Vx. On the next cycle, I charge it up to minus Vx. So the total charge is 2 times Cp Vx, right? Times 2, because I'm charging this and then discharging it, and then charging it with opposite polarity, and then discharging it. And so the net current is going to be 4 Cp Vx FLO. That's the rate I'm driving it at. So the Rp, which is Vx over Ix, looks like 1 over 4 LO Cp. So that means I could take my circuit and redraw it as follows. I have Rp to ground, Rp to ground. My op-amp, let's say this is RF, this is RF. And there's going to be some op-amp noise which I can model as, let's say, Vamp noise source. So this is the op-amp noise, equivalent voltage noise. And you can see that this basically is just a standard op-amp amplifier. The total output noise will be 1 plus 2RF over Rp squared times Vamp squared. Yes?
Is this an impedance or real resistance?
It doesn't matter. It's not a real resistance, but it acts effectively. It acts like a real resistance. Okay. Okay. Take 240. That's a quick answer. We study circuits like this in 240. But basically, since you're charging and discharging a cap through a switch, you're injecting thermal noise onto that capacitor. Okay. Now, I forgot to mention that there are some other benefits to this circuit besides the good linearity. There's also the fact that, let's put over here, I get an extra filtering stage. So let's discuss that really briefly. So usually the mixer is going to drive a filter. And typically this filter might be, let's say, 3 or 4 either op-amp RC filters or GMC filters. And so it's basically going to be a multi-stage filter. And already you can see that if I put a cap across this op-amp, so instead of putting just R, if I put a C here as well, then I have a low-pass filter. And so this acts like my first filter stage. So this is basically built into the mixer. So I can design the pole frequency here to try to knock out the adjacent channels that I'm down converting in a low IF system. Yes, question.
So in this passive current commutating mixer that we were discussing, so what will happen if we don't plug in that op amp in the last stage and just put simple resistors to convert that current into voltage?
Then we don't get the advantage, right? We want to go into a low impedance node so we don't get voltage swing at the output.
But the functionality will still
It'll still work, yeah. Effectively, then it looks like a Gilbert mixer, right? We haven't really won much if we do it that way. Okay, let's now look at diode mixers. Now, diode mixers are actually practically very important. They're used a lot for high-frequency circuits. Effectively, they're also like switching circuits, so they're like switching mixers. So what we're going to do is use the diode as a switch. Let me draw a very simple circuit, kind of an imaginary circuit. Let's say I could somehow put my RF and LO in series, for instance through a transformer winding. And let me bias up so this is a choke, let's say infinite inductance. And I bias up my diode so it's turned on and conducting some current. And the assumption here is that the LO signal is quite large, and so it can basically turn this diode on and off. So the equivalent circuit seen from the LO port doesn't see this signal here because this is the large LO choke, and so it just sees a diode. And if the LO swing is sufficiently large, it just turns this diode on and off. It looks like a rectifier, right? Half-wave rectifier. So during a positive LO cycle, the RF is connected to the output. During a negative LO cycle, the RF is isolated from the output by basically the feed-through capacitance. So this circuit multiplies RF by 0 or 1. Okay? And so it looks like a time-varying transfer function, and we get mixing action from it. Okay? Now, what's interesting is what happens if we have a weak LO. The LO is not sufficiently strong. In that case, it still acts like a mixer. We just use the nonlinearity of the diode to generate mixing products. So this is LO, this is RF. So I sum these two signals on top of each other, and basically most of my RF current would go to ground through this capacitor, and I would have an IF current going through my IF stage. Okay? So, you guys know that any kind of nonlinearity will actually generate mixing. I have LO plus RF, and then I go into some nonlinear function. I know my output is going to generate IM products like LO minus RF, which is my IF term. The difference between this circuit and the previous circuit is the conversion gain of this circuit is going to be quite a bit lower, right? Also, what's another disadvantage of this circuit compared to the previous circuit? Anybody? Let's not worry about that. Kevin? I thought you said something. Yeah, let's not worry about the coupling between the RF and the LO. The feed through and all that stuff. That stuff's nasty. In theory, we can get rid of it with a fully balanced version. But what's a big disadvantage of this circuit? Let's not worry about biasing. I mean, noise. Okay, that's valid, but something more fundamental. Maybe not more fundamental, but another problem, let's say. The problem I'm looking for. Yeah, that's it, linearity. Because we're relying on the nonlinear characteristic of this diode to generate the mixing, it's going to generate lots of mixing products, right? Why is this circuit not nonlinear? Because the diode is either on or it's off, right? So we're not relying on the diode characteristics. We're relying on the time-varying nature of the circuit. So we're always trying to build mixers that take advantage of time-varying behavior to mix rather than nonlinearity. Okay? Just came back from Boston. I almost said rather. So, okay. Let's look at a diode ring mixer. Yes.
Infinite inductor. So can we achieve this in reality? And what if like we can't do an infinite inductor?
It just needs to be large enough, right? We want most of our input signal to go through this path rather than this path. So if the impedance of this is about 10 times bigger than the impedance of this, it's going to do a pretty good job. Okay, so let me draw this circuit here. Instead of drawing it as a ring, I'm going to draw it slightly differently. So I'm going to apply my LO through this balun, my RF through this balun. I'm going to take my IF at this center tap point. And I'm going to add a couple more diodes here. D1, D2, D3, D4. Okay? So again, this is a passive mixer. It's going to have a loss on the order of about 6 dB typically. I'm going to show you guys that it has very good LO-RF isolation. It's fully balanced. And one of the downside, so these are, is that it's also very linear. Again, because we're turning on the diodes on hard, we're not using the diode characteristics. The downside is you need high LO power because diode on resistance is pretty small, right? So that you need a lot of power to drive those diodes. Compare that to a MOS device. In a MOS device, we had to drive lots of capacitance. We still had to pay for it, right? It's not for free. Even though the capacitance is reactive, we don't have infinite Q circuits. So finite Q means we had to also pay for the LO power that way. Okay? Questions about this mixer? I'm going to describe the operation in a second. Okay. Another nice thing here is because I'm using baluns, I can drive my LO either single-ended or fully differential. It doesn't matter. So this is usually sold as a standalone component where you drive the LO and RF port single-ended and you take a single-ended IF signal. It's a nice building block kind of circuit. Let's draw the equivalent circuit in the positive and negative LO cycle. Okay, so in the positive LO cycle, I have a large RF voltage here. And so let me convince you guys that this is the equivalent circuit for positive LO cycle. And furthermore, we're going to show that looking into here, we're going to see about 0 ohms. So let's look at the circuit. Okay, I have a large positive LO cycle. That means that I get a positive voltage across this winding, which is going to turn this diode on, D1 and D2 on. It's also going to produce a negative voltage across here, which is going to turn off diodes D3 and D4. Okay, so large LO turns on D1, D2, and turns off D3, D4. So if you like, I could put some tiny resistors here to model the on resistance of these guys. So this is RD1, this is RD2. And so now if you look at this circuit, because these two diodes are turned off, this node is just floating. And so here you see that it's not connected to anything. And the IF port is taken from the center tap. Okay. Now my RF signal gets applied here. And if I can prove to you that this point looks like a ground, then you could see that the RF signal appears at the IF with a gain of -1. So gain from RF to IF is -1. Actually, it depends on the turns ratio here. If I have an n-to-1 transformer, then the gain would be basically 1 over n, where n is the turns ratio. All right, so let me show you that looking into this port, we see 0 ohms. Okay. Before I do that, let me make sure this diagram is clear. Okay. So I want to show that if I look into this port here, that the impedance is very low. Even though I see basically these windings which see whatever the LO port impedance is, right? So the LO might have 50 ohms. So you would think that I should transform 50 ohms and see 2 of them in parallel. But what we're going to show is that the flux through this winding and this winding cancel out. So let me just quickly show that. So let me apply a voltage . Let's say this is ZLO, the LO driving impedance. This point is grounded, and this point comes over here. So let me apply a test voltage Vx, and note that current I1 and I2 will flow symmetrically, right? If everything is matched, then Ix will just be I1 plus I2. So I1 is equal to I2 is equal to Ix over 2. Okay. Notice that the return current actually comes from the center tap and flows back to the source here. Now V1, which is the voltage, let's say across here, is j omega M12 minus M13 Ix over 2. That's because these currents are actually in opposite direction, so that I get a minus sign here. And in fact, M12 is equal to M13 if this is designed symmetrically, so these actually cancel each other out. So V1 is equal to 0, and so is V2. So the key point is these currents are symmetric, and they both generate flux which cancel each other out. If I look at the other side of the transformer, let's say V2, I have j omega L2 Ix over 2 plus j omega, so actually let me be clear, this is V1. Okay? So V1 is ideally equal to 0 no matter what voltage I apply here, just because these currents cancel each other out, their flux. On the other hand, I could pick up V2 from the LO port. I'm not in the clear yet. But the idea is that if I look at voltage V2, let's say this is V2, then it's j omega L Ix over 2 plus j omega M23 minus Ix over 2. That's the coupling between this winding and this winding. And again, because the currents are out of phase, this goes to 0. And assuming these are tightly coupled, and similarly for V3. Because M23 is equal to M32 for an ideal transformer. So we see that this circuit does exactly what we advertised. The input voltage here is always 0, so we can replace this with a virtual ground. Okay, and that was a key point, right? Looking back here, this virtual ground allows us to say that the output is minus the RF voltage. Now for the negative LO cycle, it's very similar. Again, I have my RF. Now D1 and D2 are off, and D3 and D4 are on. And the circuit looks like this. This is my LO. Again, this is the on resistance of D3 and D4, if you like. Again, looking into here, I see practically 0 impedance. I replace it with a virtual ground. And if I take my IF stage here, I can see that now a positive voltage appears at the output. There is no phase inversion. So V out is equal to plus VRF times maybe 1 over n if the turns ratios are not equal. So again, the mixer works just as every other mixer we've seen, a fully balanced mixer. Signal RF is multiplied by plus or minus 1 at the LO rate. Okay, any questions? So we can summarize the diode. Yes?
Sorry, question. I'm not sure I understand why it's exactly symmetrical, because in one case you're looking into the P junction of the diode, in the other case you're looking to the N junction.
The reason it's symmetric is that you're basically, from the LO's perspective, you're just turning on these diodes, right? So when I have basically when I have a negative LO, I get a negative voltage here, which back biases D2 and D1, right? But it negative forward biases D3 and D4. Well, what's the equivalent circuit for an ON diode? It's just a resistance, 1 over GM, right? Plus some capacitance, diffusion capacitance. So when it's on, it looks symmetric. Now, you're actually right. If you build these in a real process, then there is a little bit of asymmetry because the PN junction 1. So how would we actually build a diode? So the way we actually build a diode, maybe let's say this is an N well, this is a P substrate, and I'll have some N plus contacts, and let's say a P plus junction. So this is a PN junction here, and this is the P terminal, this is the N terminal. Well, you'll notice that the P terminal just sees a P plus, but the N terminal actually sees a well capacitance. So the physical way that you build it does have some asymmetry, but hopefully this is not playing an important role at these frequencies. Because when the diode is turned on, right, there's two paths. There's a path through this small resistance, and then there's this path through this junction capacitance and then substrate resistance. And most of the current will take this PN junction path. So this is an integrated diode. Okay, any other questions? Well, one nice thing about this mixer is it turns out that at really, really high frequencies, it's much easier to build diodes than it is to build transistors. So if you're like trying to do something at terahertz, it's hard to find a transistor that has gain. It's hard to have a transistor that even switches on and off. But you can build Schottky diodes that work up into terahertz. And so you can build this mixer and make it work at extremely high frequencies. And because the mixer actually downconverts you to lower frequency, it's great because you get down to a lower frequency where you can actually do things. So extremely high frequency circuits usually use a diode ring mixer like this. Yes? You can. Yeah, we talked about that in I think the first lecture on mixers, right? We talked about how you could lock on to the nth harmonic of the LO. That's one way to try to get around that problem, but still the transistor needs to generate harmonics, right? And the harmonics are usually smaller than the fundamental. So if the fundamental gain is small, the harmonics are going to be tiny, and so you're not going to get much conversion gain. Okay. At high frequencies, the transformers are basically couplers. You can build the circuit using couplers. So you can use microwave structures. Okay. All right. I think that's it for mixers. Next week we'll start on oscillators.